Hello students. So today we will see regular expression. So regular expression is an algebraic notation for characterizing a set of strings, and it is useful for searching in texts when we have a pattern to search for and a corpus of texts to search through. Now let us look at different regular expression what we can have. For example, we see here a regular expression pattern what we want to find in the corresponding string. Suppose we can, so our string is, suppose we give our string as given in the textbook, interesting links to woodchucks and lemurs. So interesting links to woodchucks and lemurs. This is our string, and we want to search for woodchucks, and if we run it, it should give us a match, as you find that woodchucks is present in this particular string. But it is giving us none. Maybe we need to uh, search for just woodchucks. Then it should give us a match. Yes, there is a match. But if we have, say, similarly, we can find that at this location, it also giving at which location it is finding the woodchucks. And if we have to, we can also now, we can place a regular expression a. So it will return us the first instance where we are having the a in the text or in the string. So it gave us at position this one. At here it found the first A. Similarly, we can test it for other regular expression. So now here let us take this example. It should give us whether we find a capital or a small w. So we can make that in a square bracket. We can write and chucks. Then it should be able to give us the match. Yes, and if we give it capital W also, it should give us the match. But if we hadn't given this, then if we place it this small w, it will give us the result none, as it is case sensitive. So now similarly we can test all this. This gives us digit, any digit we can search. Suppose we place this for digit, we can say here the pattern is 1 2 3 4 5 6 7 8 9 0 in the search. So it should give us a Sorry, I think I missed one bracket. It should give us none, but if we introduce some number 1, 2, then it will return us the match. So it is straightforward. So we can have a uppercase regular expression returning only uppercase or lowercase or any single digit. So in this way we can test the regular expression. So here it is saying it should not be an uppercase. So we can also specify like this, that it should not be an uppercase by, so now it will return us the first instance where it found this. And if we give us an uppercase, it will give us W. The match is the W. So it is simple and straightforward. So you can also test it, and you can place a question mark to indicate you can have any other 0 or more character, 0 or more occurrences of the immediately previous character. Now this regular expression beg dot n, it matches any character between beg and n. So in this way you should be able to test it. And this states that start of line slash dollar end of line slash b, it gives you a word boundary. Only that particular word should be checked. For example, we want to see that only if we say would, then it will give us a match. But if we say we put the word boundary like this slash b, that means we want only would, then it will give us none. So I hope it is clear. So there is a group and precedence also. Just take a look at this and try to do some practice on your own, then you will be more clear on this. So here there is some operators which you can have, or a shorthand notation for the different expansions or regular expressions, and you can go through it and you can do some more practice on this, then it will be more clear. Okay, and try to do this. Some examples are given, some complex examples are given, try to work it out. Okay, so thank you. Hello students. So today I am going to discuss about minimum edit distance. So it calculates how the two strings are similar, and it also is useful in spell correction or spell checking. Suppose the user typed graph, and it will correspondingly it will find the closest words and corresponding alignment of the nucleotides is given. This is another application. And similarly, it can be used for machine translation, information extraction, speech recognition. So the minimum edit distance is required between the two strings, and it can be obtained through these three operations. One is insertion, deletion, and substitution. It is needed to transform one into the other. Now, for example, in the two strings given and the alignment, so we need to have this is one deletion operation, and then we need to have a substitution in these two cases, one insertion and another substitution. So altogether, if the one operation cost 1, the total added distance will be 5. And if substitution costs 2 as per Levenstein, then the distance between them will be 8. So the given a sequence of bases, this is the alignment. So now align each given two sequences, align each letter to a letter or a gate. That is the idea. So similarly, you can see this is the uh, speech recognition example where spokesman confirms senior government advisor is sought, and here it was is a substitution, this is the insertion, this is deletion operation, and this is further an insertion operation. Now there is a named entity extraction and entity co-reference. Also, it is useful to have edit distance calculated. So how to find the minimum edit distance? So we'll start with the initial state and the operators and the goal state, the word we're trying to get to, and the path cost. There are three ways we can get started with our starting word. We can have a deletion, we can have a insertion, or we can have a substitution, resulting in three different words. And in this way we can proceed, and we can get a solution space consists of several solutions, but we need to find the shortest path. We cannot afford to have all the edit sequences. So for that reason, we define a min edit distance. So what is given by di comma j. So it is the edit distance between xi comma j and yi comma, sorry, xi comma 1 comma 1 dot dot I and y 1 dot dot j. Given x and y are two strings, and we want to transform from x to y. So the edit distance between x and y is thus given by dn comma n. So now it is achieved through dynamic programming, which is a tabular computation of dn comma m, and solves problems by combining solutions to sub-problems. This is a bottom-up approach. We compute dij for small I comma j and compute larger dij based on previously computed smaller values. So compute dij for all I 0 less than I less than n and j 0 less than j less than m. So now, given this particular initialization di comma j, this is the initialization that we need to perform. Dij means I comma 0. This means from I to j, sorry, from I to 0 blank, we need in total I deletion operations. We need to have I deletion operations to get from x 1 dot dot I to blank space. And similarly, j insertion operations to go from null to, that means null to y 1 dot dot j. We need insertion operations, j insertion operations. So this is the initialization that we do, and then we declare two variable, two loops where for each I is equal to 1 to m and for each j is equal to 1 to n. We do calculate di comma j given by mean di minus 1 comma j plus 1. So we would have calculated this di minus 1 comma j, and then we will get plus 1 will give us this, and then we would have calculated di comma j minus 1, we do plus 1 will get this, and this we would have calculated this prior to that, then we will get plus, we'll do this, we will see. So for example, in order to better understand this, let me say x is given by 1 to I. and y is given by 1 to j. Now this is our I minus 1. In the first case, we have already calculated to transform I minus 1 j means we would have already calculated di minus 1 comma j. That means this is equivalent to, that means transforming x1 dot dot I minus 1 to y1 dot dot j. We would have already calculated this. That means given this, we would have already transformed into y1 dot dot j. So we then to calculated xi to j, xi, now dij means we would need x1 dot dot I to y1 dot dot j. Now already we have calculated x1 to I minus 1 to I1 to j. Now we can use that. If we have an additional character here, in order to transform this to this, we need to delete this character. We need to perform deletion operation. And that is given by this plus 1. This plus 1 indicates this is our deletion operation. We need to perform to transform x1 to I to j, because already we have this x1 to I minus 1 is computed to j. We have this given by this d I minus 1 to j. So the additional character that we have, if we perform the deletion operation, we will get this di comma j. Then further di comma j minus 1. Now again, let me illustrate this. Now we have I, x1 to I, and we have computed till j minus 1. So in order to have this extra character, we need to perform an insertion operation. So we have already calculated from x1 dot dot I to y1 dot dot j minus 1. We have already calculated, and it is given by this d comma j minus 1. So only that we need to do to accommodate this extra character is to have an insertion operation given by this. So this is denoted by the insertion operation. Now in the third case, what we have is till this point we know I minus 1 and j minus 1. We have transformed I minus 1 to j minus 1. We have already transformed, and it is given by this. Now this extra character that we have I comma j, that means this extra character that a and b. So if a and b is not equal, then we need to perform a substitution operation which will cost us 2. And if a and b are equal, then it will not cost anything, given by 0. So this will involve a substitution operation. I hope this is clear to you. So let us proceed forward. Now given this table, now I hope